Sheldon and Leonard, and in the back it says double show with our result there. Who needs a Nobel Prize after this? Okay, two remaining questions. One was hierarchy. We're very particular about hierarchy in neutrino physics. We've measured two mass differences, the solar one, the little one here, and the atmospheric one, the big one here, M3 minus M2. But the problem is that are they positioned this way or this way? We can't tell the difference because in the oscillation formula, the M3 minus M2 appears as the square. And you know that if you square a positive or a negative number, you will get the same result. So you can't tell the difference. That's one thing that needs to be done. The other thing, which is also fascinating, is what is the absolute neutrino, what is the lowest neutrino mass? We're only measuring differences, but what is the lowest mass? At the moment, there are experiments that try and measure that, not through oscillations, but through radioactive decay, what we described in the first few slides. And it's a very difficult measurement. They haven't got a result yet. All they can tell us is that the mass has to be less than 2.2 electron volts. And a new series of experiments beginning that will improve this down by a factor of 7 or so. But whatever it is, it's already very small, and it's about, say, 500,000 times smaller than the next heaviest particle, the electron. So why is there this huge gap in mass? Nobody really knows. That's, again, one of the important things to be understood. The second question that needs to be answered is, do antineutrinos oscillate in the same way as neutrinos? Now for that, you have to think a little bit about one of the biggest puzzles in nature, and that is the fact that we don't see antimatter. We see matter all around us, you, the table, the screen, everything is made out of matter. We know that there isn't antimatter in the cosmos, because if there were antimatter galaxies, they would occasionally collide with a matter galaxy, producing an immense amount of energy. We don't see that. Okay? So where's the antimatter? And should there be antimatter? And the answer is yes, because if we believe that indeed everything started with a chunk of energy at the time of the Big Bang, when energy goes into particles, it has to produce as many particles as antiparticles. So what happened to the antiparticles? Did it decay away? Now one possibility is the following. Let's go back 14 billion years. In the early universe, we believe that there might have been some very heavy neutrinos produced. When those decayed, they produced more neutrinos than antineutrinos. And when those interacted, they might have produced more protons than antiprotons. Okay? So just think, you have this many protons, this many antiprotons because of this phenomena. All the antiprotons find a mate, annihilate. And what's left are just protons. And that's you and I and the table and everything else. We're the survivors. So what we'd like to do is to understand whether there are differences between neutrinos and antineutrinos. And one such way to understand this is to look at different oscillations of the neutrino and the antineutrino. If those are different, maybe it shows that these particles are different. And maybe then we can go back and say, well, this may be a realistic step. Okay, so there's a big experiment that's about to be built to understand and explain these phenomena, and it's called DUNE, Deep Underground Neutrino Experiment. It'll send a new beam of neutrinos, again from Fermilab, through the Earth, 1,300 kilometers away, to the same mine that Davis had his solar experiment in. You see the pristine new building of physics building at Fermilab. It's probably the most beautiful physics building I know. And in contrast, you see a sort of decrepit mine there. But in fact, I should say that I took my wife down on a visit of the mine, 4,650 feet down, 10 minutes in a cage. That's the closest I came to a divorce. So the detector, which will be ready in 10 years, 34,000 tons of liquid argon and something called a time projection chamber.